Okay, hello everyone and welcome back to your YouTube channel and welcome to the very interesting video of today. As you must be aware, I am recording this special series of video dedicated to my amazing students in the course Electromechanical Conversion Systems. And for them, today we are recording this amazing video dedicated to a numerical example to one of the most important principles in the electrical machines. Today we are working with rotating machines and in particular with direct currents DC machines. So in this topic, the induced voltage play a very important role, especially when we are working or when we are specifying a DC generator. So without further delay, let me start by reading the statement that we have here. A 4-pole DC generator has a lap wound armature with 160 slots with 6 conductors per slot. The useful flux per pole is 250 milliweber. So the question here is, determine the rotational speed in revolution per minute at which the machine must be driven to generate an MMF of 200 volts. So this is a classical question that we face when we are working with DC generators. And today the most important element is to understand that there is an equation to calculate that voltage. And that voltage depends on several factors, including the number of conductors in the armature and some other properties of the winding. So let's start with the solution of this very interesting example over here. The first thing that you must notice is, as usual, I am using MATLAB script because I strongly believe that MATLAB script is one way that allow me to create this very helpful interactive document where I combine text, equation, figures, plots, but also they allow me to use code, MATLAB code, in order to focus more into the interpretation of the numerical results rather than the calculations. So here I have a very important equation. And this is the equation that I say before. This is the equation that defines the induced voltage at the armature. In this case, E is the induced voltage and the unit is volt. In this equation, on the right hand side, we have 2P, and in this case, P represents the number of pairs of poles. This Greek letter here in the middle represents the rotational speed of the armature, in this case in revolution per seconds. Here we have the useful flux per pole, in this case the unit is Weber. And then we have two very important terms that they depend of the characteristic of the winding. Z represent the total number of conductors in the armature, and C is the number of parallel paths through the winding between the positive and negative brushes. So as you can see over here, the letter C here in the denominator play a very important role. And as you can see, I put over here the two most general cases. When we are working with a wave winding, well, this letter C is equal to 2. But in this very specific case, today we are working with a DC generator And as I started at the very beginning, the armature is using a lap winding. So as you can see, Z equal to P, where P is the number of pairs of poles. So I am defining here Z is very clear, and that is the case of this problem. Now I would like to explain to you something that is very, very important, because we want to know the total number of conductor in the DC generator armature. And here I have a cross section of the armature, and you can see these very specific small spaces over here. And inside each one of those small spaces, you can see the detail over here. I am including 2 conductors. The drawing here is showing 16 slots. You can see here 1, 2, 3, 4, 5, blah, 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 16. And then we have the specific details of 2 conductors per slot. However, in this problem, we have 160 slots and we have 6 conductors per slot. So to calculate the total number of conductors in the armature, we can use this very simple equation over here. We multiply the 160 slots, and each one of them has 6 conductors per slot. As you can see, a slot with a slot cancel, and the total number of conductors, as you can see here on the right hand side, is 960 conductors. So the next step is we have been asked to determine the rotational speed at which the DC generator produces 200 volts. So what we need to do is, from this equation, we need to extract the rotational speed. So doing so, we obtain over here this very important equation. The numerator represents the induced voltage, in this case 200 volts, and in the denominator we have twice the number of poles, the flux per pole, the total number of conductors, and the letter C, that is equal to 2P. So when we put the number together, you can see on the right hand side, the rotational speed of this armature is 0.83 revolution per second. However, something very important to notice over here is, because we are using the MKS system units, I mean meter, kilogram, and seconds, so the rotational speed over here is defined in revolution per second. But we have been asked about the rotational speed in revolution per minute. So the last step here in the solution of this problem is basically transform this rotational speed 0.833 revolution per second into revolution per minute. And all my clever students, they must remember that you just need to multiply by 60 seconds in 1 minute, and you can see that the answer, the full right answer of this specific example, is 50 revolutions per minute, or 50 RPM. So we are done with this problem. In this problem, to be honest, is extremely simple example, but the most important part is that you understand over here that there is an equation that defines the relationship between the characteristic of the armature and the induced voltage. A very important term is this letter C, representing the number of parallel paths through the winding between the positive and negative brushes. When we are using the wave winding, well, C is equal to, and when we are using lap winding is twice P. Another comment regarding this equation over here before I close this video is that some of my students, they can be a bit confused, because in some books the number 2 at the very beginning here can be present or not. And the reason that can be present or not is because basically some books use P as the total number of poles instead of the number of pairs of poles. So be careful with the equation that you are using. Be careful with the units that you are using when you are solving these kind of problems and this equation. And that is the reason that I include here these very important tests to all my students to remind them how important it is to understand the theory. Well, we reached the end of this video, but before we go, I would like to invite you to be part of our community. Please follow this link over here and you will be able to find the LinkedIn and also the YouTube channel. And if you want to be updated about what is happening around the world in terms of research, development, please subscribe to the Twitter account and the Instagram account. So this is the end of this video. Today we work with the induced voltage of DC machines, and thank you very much for watching. I hope that you enjoy the explanation and you find it very useful. And I must say right now, bye now.